What specific problem does your method address regarding the loss landscape of neural networks, and how does it differ from existing research?
Our method addresses the issue of understanding the structure of the loss landscape in neural networks, specifically focusing on the existence of channels to infinity that lead to local minima characterized by diverging output weights and converging input weights. Unlike existing research that primarily discusses saddle points and local minima, we identify and characterize these channels as a novel structure that provides new computational capabilities, such as implementing gated linear units. Our empirical findings demonstrate that gradient-based training methods are likely to reach these channels from typical random initializations, which contrasts with previous studies that did not account for this phenomenon. Additionally, we show that these channels are not limited to single neurons but can involve multiple neurons, leading to higher-order derivative capabilities. This perspective on the loss landscape reveals a benign nature of non-convexity, which has not been thoroughly explored in prior work.
How does the proposed method or algorithm work? Illustrate step by step, including any novel components introduced in your framework.
The proposed method involves analyzing the loss landscape of neural networks, particularly focusing on the phenomenon of channels to infinity that arise from neuron duplication. Step 1 is to initialize a neural network with a single hidden layer and train it until convergence to a finite norm local minimum. Next, the method applies neuron duplication, which creates a saddle line in the loss landscape, characterized by critical points that maintain equal loss values. The third step involves using an ODE solver to integrate the gradient flow dynamics, revealing channels where output weights diverge while input weights converge, leading to local minima at infinity. A novel component introduced is the identification of these channels as implementing gated linear units, which enhance the network's computational capabilities, allowing it to achieve better performance in various tasks.
Can you provide a concrete example that demonstrates the inner workings of your algorithm, particularly how channels to infinity are formed and utilized during training?
A concrete example demonstrating the formation and utilization of channels to infinity during training involves a multi-layer perceptron, MLP, with two neurons. Initially, the network is trained until it converges to a finite norm local minimum. Following this, neuron duplication is applied, creating a saddle line characterized by diverging output weights of the duplicated neurons and decreasing distances between their corresponding input weight vectors. As the training progresses, the gradient descent dynamics often converge into these channels, which are extremely flat along the saddle line, allowing the network to implement a gated linear unit. This process illustrates how the channels to infinity not only provide a pathway for the optimization process, but also enhance the network's computational capabilities by enabling it to approximate complex functions effectively, as seen in the empirical results where the loss continually decreases along these channels.
What theoretical or practical benefits does your method offer over traditional approaches to training neural networks, especially in relation to convergence and generalization?
Our method reveals the existence of channels to infinity in the loss landscape of neural networks, which are characterized by diverging output weights and decreasing distances between input weight vectors. This structure allows gradient descent dynamics to converge to these channels with high probability, providing a pathway to local minima that are not only stable, but also implement gated linear units, enhancing the network's computational capabilities. Unlike traditional approaches that may get stuck in local minima, our findings suggest that these channels facilitate a smoother convergence process, as they are extremely flat in certain directions, which can improve generalization. Additionally, the channel's unique properties allow for the exploration of new solutions that traditional methods might overlook, potentially leading to better performance in tasks such as model fusion and continual learning. Overall, our approach offers a deeper understanding of the loss landscape, which can inform more effective training strategies for neural networks.
How was the method validated in your work? Please describe the experimental design, datasets used, and the performance metrics that were applied to demonstrate the effectiveness of your approach.
In our work, we validated the method by conducting extensive empirical investigations using small neural networks with varying architectures, specifically focusing on a scalar regression problem in a two-dimensional input space. We trained these networks under different conditions, including varying layer sizes and input dimensionality, across multiple datasets, such as the modified Rosenbrock function and Gaussian processes with different kernel scalings. The performance metrics included the probability of reaching channels to infinity and the convergence behavior of the networks, which we assessed through loss values and the stability of solutions found. We observed that many saddle lines contained plateau saddles where gradient dynamics converged, with probabilities ranging from 10% to 30% across random initializations. Additionally, we analyzed the eigenvalues of the Hessian to differentiate between finite norm solutions and channels, confirming that channels became sharper and flatter as training progressed, indicating their effectiveness in leading to local minima at infinity.
What are the main limitations or potential drawbacks of your method, particularly in terms of applicability to larger or more complex neural networks?
The main limitations of our method, particularly regarding its applicability to larger or more complex neural networks, stem from the empirical nature of our findings and the specific setup we utilized. Our theory was developed for a single hidden layer MLP with mean-squared error loss, which may not fully capture the complexities of deeper architectures or those using non-smooth activation functions like ReLU. Additionally, while we observe channels to infinity in various architectures, the quantification of their occurrence probability in large-scale models, such as transformers or convolutional networks, remains an ongoing area of research. Furthermore, the channels we identified may not generalize well to networks with biases, as empirical evidence suggests that adding biases significantly reduces the presence of plateau saddles in the loss landscape. Lastly, the flatness of these channels could lead to optimization challenges, as commonly used optimizers may get stuck at the beginning of a channel, limiting their effectiveness in finding optimal solutions.